Assalamu alaikum. So today, inshallah, we'll continue on the same subject about the spatial and frequency domain filter design. And if you remember last time, we have said that for the filters, we may use two main types of filters. We have the spatial domain filter, in which we are applying the filter in the spatial domain without the need to transfer it or to transform the image to any other, let's say, space. Or we have the frequency-based filter design, where here in this case, the first step is to convert our image from the spatial domain or the spatial space to the frequency space, okay, to the frequency domain. Then after this transformation, I can apply the filter, and after applying the filter, I can make the inverse transform again, okay? So, if you remember last time, we have started considering the spatial domain filter. We have said that this spatial domain filter, if I will apply this filter in the spatial domain, I need to apply the convolution operation. Convolution operation between what and what? Between the image and the kernel of the filter itself. Okay? And we have said that this kernel, it may have a small size. Most of the cases it's something like this. It's a square size. It's m by m. What m here in most of the cases is an odd value. Okay? Examples for the sizes of the kernel, we have 3 by 3, for example, 5 by 5, 7 by 7, and so on. It depends on the type of the kernel that I want to apply. Okay? And within this spatial domain filter, we have said that we have these 4 types of filters. We have the averaging, or we call it mean filter. We have the median filter. We have the Gaussian smoothing and conservative smoothing. Right? So, let's go directly to the types of the filters. So here, if you remember, we have said that this slide, it shows several things in the same place. Here, first of all, we in part A or in image A, here we have an example of an averaging filter kernel. Okay? The idea here is the following, which is that, as you know, if I will apply this filter, I will use the convolution. What do I mean by convolution? I need to make a shift, multiply, then add. Right? So here, as you can see, in most of the cases, our filters are symmetric. Okay? So in this case, in most of the cases, the filter is symmetric. So in this specific case, I don't need to make the shift. I can apply the multiplication directly, then I can make the addition. Okay? So how the addition will be applied? Actually here, this filter, it will be applied in each pixel of the image. Okay? Pixel by pixel. Okay? And the pixel of the image in which I'm applying this filter, it corresponds to the center value here. Okay? And the other values, actually, it will affect the neighborhood of this pixel. Right? So each one of these values, actually, it will be multiplied by its corresponding pixel. Then after that, the result of the multiplication will be added up in order to give me an information about the new value of the pixel. Okay? And as you can see from here, what will happen is that as if I am adding all of the pixels, including the pixel itself and the neighborhood, and after that I'm dividing by the number, which is 9, which is exactly what is the average, okay, or the mean. So this one type of filter, which is in figure A. In figure B here is showing the concept of the median filtering. The median filtering here as well, I will consider, actually it doesn't have a kernel, but I have a certain algorithm that needs to be applied on the pixel and its neighborhood. So I will take here the pixel with its neighborhood having the size of A by 3. I will sort out the values of these pixels, and I will take the middle value, which is called the median value, and it will replace this pixel. Okay? So in this case, what will happen here, I have the values that are ranging from 100 up to 153. Okay? They will be sorted out. So in this case, I will have 9 sorted values. I will take the 5th element after sorting, and this will be the median. Okay? And the 5th element here is the red one, which is 103. So this pixel, it will be replaced by 103. Understand the idea? Right, so this is one thing. Another thing here we have in figure C. Figure C actually is, we can say, an enhancement, or let's say, an improvement over figure A. So instead of using the averaging, here I will use something which is called what? Gaussian smoothing. Okay? Its corresponding kernel here is in figure D. Okay? Here, as you can see, what is the size of this kernel? Here I have a kernel of bigger size, it's 5 by 5. Okay? And as you can see from here, that the weights of the different elements, they are different as well. Okay? Only the element at the center has the maximum weight. And as I go away from the center, the effect decreases. Okay? In this case, actually, I'm doing the average, but it is a weighted average. Okay? If the pixel is near to my pixel, in this case, the contribution will be high. If it goes further, the contribution will be low. Understand again? So this one type of, let's say, yes? Yes, why we divide by 273? It is the total, exactly. Because actually here what I need to do is the following, which is that if you look at the averaging or even the Gaussian smoothing filter, you will find that the total number of the values that exist here in the different locations, if I sum them up, they should sum up to 1. Okay? Right? So here, what will happen is that, for example, in this top left corner, its value is equal to 1 divided by 273. Okay? This center value, actually, its value is 41 divided by 273. If I will add all of these values together, it should sum up to 1. Same thing can be said here for the averaging filter here in part A. Okay? Right. Also, we have said that for the averaging or mean filter, we were faced with two main disadvantages. Remember? I will just bring the slide. We have two problems here. We have two problems. What are these problems? Do you remember?
It's getting rid of the sharp edges.
Yes. This one thing, which is that if I will make, let's say, an average for the pixel using its neighborhood, this means that if I'm going to straddle, as we say, that if I'm going to cross a certain edge, this edge will be blurred. Okay? This edge will be hazy. I will not be able to define it anymore. Okay? This is one thing. Another thing here, which is in the first point here, if I have one of the pixels that exist in the neighborhood that has an unrepresentative value, this means that it has a certain noise value or big value or very small value with respect to the other pixels, it will have an effect. It will significantly affect the value of the average. Okay? So this means that I'm introducing values that does not exist in the image itself. Okay? Here, as you can see, the averaging, we can consider the averaging is a low-pass filter or high-pass filter. What do you think? Low-pass filter means it's a filter that can allow only the low frequency to pass. Okay? And it will suppress the high-frequency components. The high-frequency, the high-pass filter is the opposite. It will allow the component with high frequency to pass, while the low frequency component actually will be suppressed. Okay? So in this case, what do you think?
High pass. Yeah. High pass.
What do you think?
High pass.
It's a high pass or low pass? And why?
It's high because the problem is that some of the pixels will get more values, so the noise are high values, so it allows the high values to pass.
Allows the high values to pass. Yes. What do you think?
The noise is a high frequency, so we need to remove this high frequency.
We need to remove this high frequency. Can the average or mean filter can remove this high frequencies?
Mm-hmm.
What do you think?
All the pixel is high,
Yes.
so it will be a high frequency.
Okay. So let's put it in another way. Let's assume that I have this figure. we say that here in this image, image number A, we have here the original noisy image, right? Okay? And in image number B, we have the filtered image after making the averaging. Okay? So here we say that in most of the cases, the averaging, it will make some sort of smoothing. What's the meaning of smoothing?
I will be low and
This means that I will try to reduce the variations as much as possible. Right? Smoothing, this means that if I have, for example, a certain neighborhood that contains values of high values and low values, etc., what I need to get is the average of all of these values together. Okay? So this smoothing effect actually, it is something like the low pass filter effect. It's something by low pass filter effect. This means that the variations here, actually they will be smoothed down. Okay? I will not have these variations anymore. And as proof of this, if for example I have a clear edge that appears in a certain image, and I pass or I make an averaging of this image will be blurred. The blurring of the edge actually, or the edges that exist in this image, this means that the high frequency that corresponds to the edge has disappeared now. So I will not be able to detect the edge anymore. Or let's say it will be more difficult to detect the edge than before applying this average filter. Do you understand the idea? So, in conclusion, we can say that the averaging filter or the mean filter, average and mean, they correspond to the same thing. Okay? Averaging filter or mean filter is a smoothing filter. That is to say, it is a low pass filter. It allows the low frequencies to pass, but it will suppress the high frequency. And with this high frequency, it includes both the noise and the edges. Okay? Right? So the edges here, actually, it's an abrupt change in the values of pixels. Abrupt change, this means high frequency components. Noise as well is high frequency component. So here in this case, if I will apply this averaging, it has the, we can say, the advantage of removing some of the noises that I have in the image, but on the other hand, the disadvantage is that it will remove the information about the edges as well. Okay? So here in this figure, he's showing us, as you can see here. In the first image, he has added a noise according to Gaussian distribution, and in the second image, which is image C, he has added the type of noise that's called salt and pepper. Okay? And here in B and D, B actually is the result of filtering A, and D is the result of filtering C, using the averaging filter that we have. Okay? So we have these two problems. The next filter that we have discussed was called the median filter, and in this median filter, they are claiming that both of these two problems can be reduced significantly. Okay? The problem of having unrepresentable values in the average, and the problem of, let's say, smoothing out the edges. Okay? So here we say that the median filter is normally used to reduce noise in an image, somewhat like the mean filter. However, it often does a better job. Okay? So here, we say that both of the problems related to the mean filter that we have discussed before can be resolved. We will not say that they are resolved 100%, but it is resolved to a high extent. But on the other hand, this filter, if I will, let's say, compare the complexity of using this filter or the computation of this filter with the computation of the previous filter, which is the average, which one of them is more complex? The median or the average filter? Median, why? I need to sort, okay? And this sorting technique, as we have said before, most of the cases we may have sorting techniques that are having complexity of n squared, okay? In some better, let's say, sorting techniques, we may have n log n, but still, this is a high complexity if we compare it with the complexity of the averaging filter. Okay? Right. So
So we say that the median filter considers each pixel in a neighborhood in the image and replaces it with the median of the values that we have. Okay? And here we say that this median filter is very desirable, especially for salt and pepper. And let's see here. Let's look at the images.
Here again, this image number A. Here in this image we have added a noise which according to the Gaussian distribution. Okay? And in image C, here the noise that is added is salt and pepper. Okay? And the noise B, this is the result of filtering, in image B, this is the result of filtering image A. As you can see here, I have some sort of smoothing. Okay? But if we look at the quality of image D, which is the result of filtering the salt and pepper noisy image, actually you'll find that it has a high quality, as you can see. Okay? So the median actually is very, very, let's say, suitable for the case of salt and pepper. Yes?
We currently have a noisy picture.
Yes.
Then we add the noise filter. So you can filter?
No, actually here in this case we have the original image and we have the noise, we have added the noise ourselves.
Yeah.
Okay?
How
But in real life, actually the image will come with its noise. Okay? Which with the undesirable values that are added to our image. Okay? Which may be of different sources, as we have seen before. Maybe, مثلا, one of the sources may be the environment itself. The weather, for example, is sandy, or we have, let's say, rain or something like this. Maybe I may have, for example, due to the capturing device itself, it may be مثلا of cheap, let's say, brand or something like this. So it may add some noise by the capturing device.
we can filter it or
We can filter it, yes. We can filter it as well. Okay? We can filter it. But here, what we are trying to do is that here we are simulating the case. Here we have the original image. The image is not noisy at all, okay? Doesn't have a noise. And we have added the noise ourselves. And we have added two types of noise. And we are trying to see what will be the effect of applying different types of filters on these different types of noisy images. Okay? Do you have any questions so far? So here, if we look at the previous slide, we say that advantages over the mean filter, advantages of the median filter over the mean filter. We say that the median is a more robust average than the mean. And so a single, very unrepresentative pixel in a neighborhood will not affect the median value significantly. This unrepresentative value, we have said that it is either very high with respect to its neighborhood or very low with respect to its neighborhood. So after making the sorting and everything, actually this will be considered as an outlier value. I will not consider it at all. It will not appear in the filtered image. Okay? So like this I have got rid from the, what we call it, the outlier values. Here also we say that since the median value must actually be the value of one of the pixels in the neighborhood, so this means that there is a big possibility that I am preserving the information about the edges. Okay? Because actually the median is, if you look at the median value, actually it's value of one of the pixels that appear in the neighborhood. Either the same pixel in which I'm applying the filter, or one of the pixels that appear in its neighborhood. So this means that there is a big possibility that I am preserving the information about the edge. Right? Okay. The only disadvantage here is here we say that it is relatively expensive with respect to computation. It needs more time to compute, especially if I have, for example, large images. Okay? So this means that for each pixel I need to make sort, and I need to take the median and repeat this operation for all of the pixels that I have in the image. But let's look at the Gaussian smoothing. The Gaussian smoothing is somehow similar to the averaging, but here we have said that for our kernel, the weight of the different points in the kernel actually will be different. Okay? So the center point will have the maximum weight, and as I go further away from this center point, the weight will decrease. Okay? According to this relationship. You know the Gaussian distribution, it has the bell-shaped curve. Okay? So the Gaussian smoothing operator is a 2D convolution operator. Sorry. That is used to blur, or let's say to smooth images and remove detail and noise. Here the detail, by detail here I mean the edges. Okay? So actually it will remove both. It will remove the edges and it will remove the noise.
So in this case here, I need to make some sort of trading off. Okay? In this sense, it is similar to the mean filter, but it uses a different kernel, okay? which represents this bell-shaped curve. So here, the idea of the Gaussian smoothing is to use this two-dimensional distribution as a point spread function. What do I mean by a point spread function? This means that it's a function that starts at a certain point with very high intensity, and as I go further, it starts to fade out. Okay? That's what's meant by point spread function. And this is achieved by convolving the kernel with the image. After creating this kernel according to the Gaussian distribution, I will convolve it with my image. Okay? The normal way that we are used to. Okay. Here is saying that we have, in real life, the Gaussian distribution is a non-zero everywhere. So this means that as I go, for example, for infinity values, okay, I will have value for this Gaussian distribution. It has this bell-shaped, but it is decreasing gradually. Right? It does not reach zero, actually. Okay? But we make some sort of approximation, depending on what? The things that can describe any Gaussian distribution is the mean value. Where is the mean value? And another value which is called what? What do you think? How can I describe the Gaussian distribution? If we look at this equation again. N node and N node, these are the average values, okay? One of them is in the horizontal direction and the other one is in the vertical direction. What else? في symbol هنا ظاهر غريب. Sigma. What is this sigma? Standard deviation, exactly. Standard deviation, okay? What do I mean by standard deviation? What does it measure, in fact? Yes, how the elements are dispersed around the mean. Okay? So, for example, if I have a standard deviation that has a high value, relatively high value, so this means that I have big fluctuations in the values of the points that I have. If I have a standard deviation with a low value, so this means that the fluctuation is smooth. So here we can say that as an approximation, because here actually I am using a finite system. And this matrix should have a finite size, as you can see, either 3 by 3 or 7 by 7. I don't have the luxury of having infinite values or continuous values. So here we are using this property. We say that Gaussian distribution is non-zero everywhere. We know this, which would require an infinitely large convolution kernel. But this is not possible. In practice, it is effectively zero more than about the 3 standard deviations. So if I have a sigma of standard deviation, if I go away from the mean value by a value that is greater than 3 times the standard deviation, the values of the distribution actually can be considered as approximately zero. Okay? So here we say that in practice it is effectively zero. Here I am talking about the value of the distribution itself, more than about 3 standard deviations from the mean. As I go away from the mean by a value that is greater than 3 values of standard deviation, I can consider that the distribution has the value of 0. Okay? So we can truncate at this point. Okay? In this case, I can use some, we can say, kernels with finite size. And here is saying that another thing which is the standard deviation can affect my smoothing in is that the degree of smoothing is determined by the standard deviation of the Gaussian. Okay? Like if I want to compare the average filter with the Gaussian smoothing filter, we can say that the average smoothing filter is a special case with the Gaussian smoothing, right? But its standard deviation is equal to how much? It's very big, right? It's very big, and it's almost infinity, right? That's why here I will find that all of the points in my kernel are having the same value. They will not decrease. Since the value will not decrease and they will have the same value, this means that the standard deviation is very high. Okay? So here we say that the degree of the smoothing actually is determined by the value of the standard deviation.
So can you repeat the point?
Yes. Here I'm talking about the comparison between the average kernel and the Gaussian smoothing kernel. Okay? Here, we know that for the this is, for example, this is the Gaussian distribution, right? Okay. For the average distribution, it's something like this. Okay. So for the average distribution, we can say that the average distribution is a special case of the Gaussian distribution, but having a sigma that's equal to how much? Almost infinity. Okay? Since, as you can see here, the distribution will not decrease. As I am going away from the mean, actually the distribution is not decreasing. Okay, so here we can say that sigma is very high. So if we look at this Gaussian smoothing kernel, we'll find that it's a two-dimension, of course. Don't forget that all the time here we are dealing with two dimensions. Here we have these values for the mean, and the sigma here is equal to 1. And sigma here is equal to 1. If I will increase the sigma, what do you expect to have here as values at the boundaries? What will happen to these values if I will increase the sigma? These boundary values, will it increase or decrease? What do you think? If sigma increases, okay? What do you expect to happen, for example, at these corner values? Will they increase or decrease? They will increase. They will increase. Why? Because actually the fluctuations actually will increase, right? So the possibility to have bigger values here, actually, it will increase as well, okay? And vice versa. If sigma decreases, this means that here my distribution will be something like this. So I'm expecting that the values that will appear here at the boundary actually will decrease. Okay? Fine, let's look at this figure. Yes, have a question? Yes, here, considering the sigma here we have said that the sigma, it measures the fluctuations around the mean. So if the fluctuation increases, this means that the values that are away from the center, or let's say away from the mean value, will increase as well. Okay?
For this slide, you say when the sigma is 3 times, the standard deviation, then it goes to 0.
Exactly.
So what's the relation that they will increase now when the sigma?
Yes, here I'm talking about how I am going to make the variation with respect to the value of sigma. Here we have said that if I go 3 times the sigma away from the mean, this means that it will be equal to 0, right? But here I'm talking about this same fixed point. What will happen to it if I will vary the value of the sigma? Okay? So for this same point, if I will, let's say, increase the sigma, I expect that this point value will increase. Right? What will happen to the center value if the sigma increases? The area under the curve here should be equal to 1. Right? So here I am having something like this. So this is one distribution. Okay? If I will increase, let's say, the sigma, distribution will be something like this. If I will increase the sigma more, distribution will be something like this, and so on. So here what will happen is that as sigma increases, I will find that the values of the different, at the different points of the distribution, they will become near to each other. Okay? As a level. Right? Okay? But of course here the fluctuations are big. See? Now try to think about it. I think you have already studied this kind of distribution before, right?
Yes.
Okay. But let's see here an example. As we will see after a couple of minutes, we'll see it on the MATLAB as well. Here we have, again, we have our 2 images. Once here we have added the Gaussian noise, and now here we have added the salt and pepper. Then after that, for these 2 images, I will apply the Gaussian smoothing filter. Okay? So as you can see here, we have, I think you can notice the smoothing effect, right? You can actually, in both of these 2 figures, maybe this one actually it is much more clear. So here, D, this is the result of applying the filter on image A, and D is after applying the filter on image C. Right? So as you can see from here, we have eliminated some of the noise, okay? But as well, we have eliminated some of the edges, right? That's why here he's introducing another type of smoothing, which is called what? Conservative smoothing, okay? Conservative smoothing. In this kind of smoothing, the idea is that the elimination, maybe the elimination of the noise will not be that big as in the case of the average, okay? But on the other hand, I will gain the property that I will be conserving the information about the edges, okay? So how it works? We say that this type of smoothing is conservative يعني محافظ, okay? It does not remove the high frequencies blindly, like it's saying here, okay? Right. So there are two conditions to be tested before a replacement could be made. Here in this case, I don't have a kernel, I have an algorithm. It's like the median filter. Okay? Here is saying that first a neighborhood is selected around the pixel under study. So in this case, I will consider the neighborhood of the pixel. So here, if I will consider, for example, a 3 by 3 part, so for the center pixel, I will have a neighborhood of 8 pixels. Right? And for these 8 pixels, I will determine what is the maximum and the minimum for the 8 pixels without including the pixel itself. I will consider what is the maximum and what is the minimum. Okay? So here, the minimum and maximum value from this neighborhood is found, and the center pixel value is compared against these limiting values. If the value of the center pixel is above the maximum, then it is set to the maximum value. Okay? Or if it is less than the minimum, then it is set to the minimum value. Else, it will remain as is. Let's take an example here. Let's consider these two cases here, okay? So now I have this set of pixels, as we have said before. This is the pixel at the center that has the value 153. This is the pixel under consideration. In this case, I will consider only its neighborhood, without considering the pixel itself, first of all. And in this neighborhood, here I have how many pixels in the neighborhood? I have 8. I will consider what is the minimum and what is the maximum. Okay? So here, what is the minimum value here? Here it is 100, right? And the maximum is 105. Okay? Now I will look at the pixel itself. If I will find that this pixel is greater than the maximum, this one will be replaced by the maximum. Okay? Like in this case, for example, if I have this pixel, it is less than the minimum, so it will be replaced by what? By the minimum. But if it is between the minimum and maximum, keep it as it is. Keep it as it is. Okay? So like this, I have eliminated a part of the noise, but I have kept the information about the edges. Okay? So in this case, you will find that if you look and if you make a comparison between this type of, let's say, filtering with the averaging and the Gaussian smoothing, we'll find that here the elimination of noise is not that efficient. But on the other hand, I have reserved the information, the main information around the edges. Okay? So here, this one is called conservative smoothing. So here we'll find these are the results. Slightly better. Here, after filtering, here as usual, we have these two images, A and C are the images having the Gaussian noise and the salt and pepper. B and D, these are the images after the filtering. Okay? Part of the noise has been removed. Okay? But still the image is, yes, it's noise, it's still noise. Okay? But I have, here we need to make some sort of trade-off. What is the thing that is much more important for me? Okay? Do you have any question about this part? So this is the end of what we call it the spatial domain filtering. Okay? Spatial domain filtering. As you can see here, we didn't need to do any transform of the image. We have applied the filter in the spatial domain using the convolution. Okay? Any questions here? Now let's go to the second type of filtering, which is called the frequency-based filter design. So this means that I will apply the filter in the frequency domain. As we know before, that the convolution in the spatial domain is corresponding to what in the frequency domain? Multiplication. Okay? Multiplication. So what will happen here actually is that I have the image and I have the filter kernel. Both of them I need to make a frequency transform for them using the fast Fourier transform. And after applying the fast Fourier transform, I will multiply these two values together. And that's it. Okay? What's remaining is just to make an inverse transform back again in the spatial domain. Okay? So here, what do you think about, here, in the previous case, in the case of the spatial domain filtering, we have an image, let's say, of dimension R by C, and we had a kernel of M by M, and we made a convolution between them. Right? Now what will happen is that I will apply the Fourier transform on both the image, let's call the image, I will call it small f, and this one is called small h, and I will apply to them, both of them, I will apply the Fourier transform. So in this case, I will have, for the image, I will have f with a certain dimension, and I will have the, let's say, the filter transform as capital H. Okay? To make the multiplication, actually here it will be a multiplication of element by element, in which we'll use this operator. Okay? To use this operator, what is the condition that should be respected here with respect to the dimensions of these two matrices? They should be the same size. The number of columns equal to a number of rows. This if I will use the regular multiplication of matrices. But here I need to make element by element. This means multiply the first element by the first element, second by second, third by third. Okay? So in this case, both of these two matrices should be of the same size. This means that this kernel, its size after conversion, should be changed to the size of the image itself. Okay? And as you will find in the MATLAB, we have the function that's called FFT2, which is the fast Fourier transform 2. You will find that here I have the matrix that needs to be transferred, as well as some information about this size. So you will say that here, for example, you want to make a transform, okay? And what will be the size of the transformed image or the transformed matrix that you want to do? Okay? So in this case, you can specify the same size for both the image and the kernel itself. So that after that, we can make the multiplication. Okay? So both of these two matrices, I will apply the element by element multiplication operation. And the result of the multiplication, I will do on it the inverse Fourier transform, and that will be the end of our operation of the filter. Okay? So here we say that frequency filters process an image in the frequency domain. So here our operation of the filter will be in the frequency domain. Okay? So the image is Fourier transform multiplied with the filter function that is also in the Fourier transform after applying the Fourier transform on it. Okay? And then re-transformed back into the spatial domain. Okay? So here we say that attenuating high frequencies results in a smoother image in the spatial domain. Attenuating low frequencies enhances the edges. Again, here when we attenuate this means reducing. Okay? So here when we reduce the high frequencies, reduce the high frequency components, this means that I can remove the noise and I can make smoothing of the image. Right? But if I will reduce or attenuate the low frequencies and keep the high frequencies, this means that I'm interested in finding where to find the edges. Right? Okay? Because actually the edges here, they correspond to high frequency components. Right. So you say that this is based upon the product of Fourier transform, that the convolution in spatial domain becomes multiplication in frequency domain. So in this case, it will reduce the computation required for filtering process by 2/3. How comes? How if I will make this in the frequency domain, it will reduce the filtering process by 2/3. Of course, here it didn't count the time needed to make the transform. Okay? Here in the case of the convolution, we have said that I need to do three things. Shift, multiply, then make the summation. I have three operations that needs to be done for each pixel. But here for each pixel, I need just to do one thing, which is multiplication. Okay? So that's why here it's saying that the operation will be reduced by 2/3. This is not an accurate, let's say, argument, because actually here he didn't take into consideration the time needed for the transform and the inverse transform. The fast Fourier transform and the inverse fast Fourier transform. And here we say that the transformation and inverse transformation, of course, here are needed to be done as one type process at the two ends of the process block. First, make the transformation, and at the end, I need to make the inverse transformation. And in between, I will make the multiplication. So here it's showing us in the spatial domain. Here I have the image F will be convoluted with the kernel H to get the filtered image G. Okay? This corresponds in the frequency domain, is that both of them are Fourier. I will apply on them the Fourier transform, and the resulting transformed values will be just multiplied in order to have the filtered image. Then after that, I can make the inverse transform again. Okay. Here is saying that all frequency filters can be implemented in the spatial domain with this condition: if there exists a simple kernel for the desired filter effect. Okay? It is computationally less expensive to perform the filtering in the spatial domain. Okay? Because actually here, as we have said before, I need to make fast Fourier transform. Okay? So here is saying that if I have the frequency filters can be easily implemented in the spatial domain, it is better to apply the filter in the spatial domain. Otherwise, apply it in the frequency domain. Okay? So here we say that frequency filtering, on the other hand, is more appropriate if no straightforward kernel can be found in the spatial domain. For example, if I cannot figure out what will be the shape of the kernel in the spatial domain, in this case it's better to do the filtering in the frequency domain. Because in the frequency domain it will be somehow graphical. Okay? When I have the fast Fourier transform, I will have something like this. And I will assume that the highest frequency, the zero frequency will be at the center, and the frequency component will increase as I go away from the center. Okay? So in this case, how can I do my filtering? It will be straightforward. I will have another, let's say, مثلا mask filter of the same size, in which here, مثلا, if I am interested in the low frequencies, so I will have a disk like this at the center that has white values at the center and black values all around. Okay? If I want to make, this is for the low pass filter, right? So in this case, if I will multiply this filter by the image, the low frequency component will be preserved and the high frequency component will be removed. If I'm interested in detecting the edges or to make high pass filtering, in this case what I should do? I will do the same thing. But here in this case, the disk, the part inside the disk will be black, and the part outside the disk, which corresponds to the higher frequencies, actually will be equal, will have white values. And then after that, I will do no multiplication, and that's it. Okay? So like this, it will be much easier to do it in the frequency domain, as you can see. Okay? Instead of trying to figure out what will be the value of the kernel in the spatial domain. Okay. Here is saying that the form of the filter function determines the effect of the operator. So there are basically three different kinds of filter. We have the low pass filter that will allow the low frequency components to pass and suppress the high frequency components. We have the high pass filter, which is the opposite. And we have the band pass filter that suppresses some of the low frequency components and some of the high frequency components. Okay? So like this band pass filter can be used, if I want, for example, to remove the noise and at the same time keep the edges, the information about edges. Okay? Of course, this needs some sort of trial and error. Okay, and try to see what will be the best band pass filter that can be applied so that the signal to noise ratio will be as maximum as possible. Okay. Here is just giving us some information about the low pass filter. We say that it attenuates high frequencies and it is used mainly for smoothing and noise removal. Okay? And the high pass filter, on the other hand, it yields edge enhancement or edge detection. Here actually I am conserving just the high frequency components and removing the low frequency components. Okay? And the band pass filter here, it can be used to enhance edges and at the same time reducing the noise. Okay? This is the most difficult type of filters here. The design of this type of filters actually is the most difficult type. So here we say that it attenuates very low and very high frequencies, just very low and the very high frequencies. So how can I represent it here? I want to attenuate the very low frequencies and the very high frequencies. So in this case, I may have a small circle here at the center, and I may have, for example, a bigger circle, something like this. And this will be the black part, this will be a black part, and this is the only frequencies that needs to be passed, or the frequency that I will allow them to pass. Okay? Okay. So here, what we'll see next, the application of this frequency-based filter in the frequency domain. So here we said that the most simple low-pass filter is the ideal low-pass filter. What do I mean by ideal low-pass filter? The one that has sharp cutoff frequency. Okay? I have a cutoff frequency of F node. All frequencies below F node will pass, and the frequency above F node actually will not be allowed to pass. This type of filters cannot be implemented in real life. Okay? We don't have this kind of sharp edges, but we may have some other types of filters as we see. So here we say that it suppresses all frequencies higher than the cutoff frequency and leaves smaller frequencies unchanged. And so essentially, it's like a masking operation where a circle of all ones is ended with the Fourier transformed image, something like this. Okay. Here, a better approach is to use a gradual cutoff shape, such as the Gaussian mask. Okay? Instead of having مثلا here, if we consider that this is the frequency and this is the amplitude that will be allowed, or the gain of the low-pass filter. Let's assume something like this. This is the ideal type of low-pass filters. Here I have F node, something like this. Okay? Of course, the better one is the Gaussian, and this one is much more practical. It will be something like this. You see? So here we will see in this figure, this filters in the frequency domain. You will have something like this. So they showed us the, here, this is the frequency, representation in the frequency domain of the sharp cutoff frequency filter, and this one is the Gaussian. As you can see here, we have certain waves, okay? This means that it is not just decreasing gradually, okay? Decreasing gradually, this means that it is a non-increasing function, right? But actually here in this case, actually it is increasing and decreasing. This kind of waves, actually it happened due to the effect of having a finite filtering, okay? So as a result of this, actually we will have this kind of transformation from the spatial to the frequency. We will have some such kind of waves.
this kind or this values of waves, they will appear at the boundaries, as you can see here. So this is the frequency representation, or let's say the representation of the signal after making the transform, the three-dimensional plotting. And this is the same value, but using the two-dimensional plotting. Okay? For here we have x and y, where x and y here they represent frequency values. Okay? Here at the center, as we have said before, this corresponds to the minimum frequency, the zero frequency, and as we go away from this center, we'll have the frequency will increase. Right? So, what will happen is that I have my filter in the frequency domain. I will make the transform of my image in the frequency domain as well, and I will multiply this filter with the image that I have. And after that, the result of the multiplication, I will make on it the inverse Fourier transform. So here, let's consider this example. Here we say that this is the Gaussian noise corrupted image, which is image number E. Right? And F, this is the fast Fourier transform of image E. Okay? And as you can see from here, since this image is noisy, you will find here at the high frequency region, you will find white dots. White dots, okay? If you will make, for example, the transformation of the original image before adding the noise, we'll find that these white dots actually they don't exist. Okay? What I want to do here is to remove these white dots. Okay? Image G, this is the filtered image using the filter with the sharp cutoff. And image H, this is the filtered image using the image with the Gaussian distribution. Okay? So, this is the same thing here, but instead of applying Gaussian noise, here we are applying salt and pepper in image A. Okay? This corresponds to the transform of the image using the fast Fourier transform. This is represented in image B. Then C, this is again the result of filtering the image using the sharp cutoff and using the Gaussian distribution. Okay? Using the Gaussian smoothing image. Right. Now, before switching to the MATLAB, do you have any questions about this part? I need to apply this on MATLAB. So what will happen here actually as a filtering in the frequency domain, it is very simple. Get this fast Fourier transform image and multiply it by the fast Fourier transform of the filter that you have. Okay? And after that, the result of the multiplication, just do in it the inverse fast Fourier transform. Okay? So like this, you will obtain the filtered image. Right. So we'll go through the examples that we have here, okay? We have this one, RGB, We'll start first of all by the spatial filter. Then after that we will switch to the frequency domain filter. Control V. So here in this part, so here in the first part we will see examples of applying the spatial domain filters, which were the average filter, the median filter, the Gaussian smoothing filter, and the conservative smoothing filter. Then after that we will see the result of applying this filter, especially the Gaussian smoothing filter and the sharp edge filter in the frequency domain. So we'll see the effect of applying the Gaussian filter in the frequency domain. And here, as a first step here, we are just trying to create the filters that we need. Here, H1 here. H1 here is what type of filter? It is ones. Here when we say ones, 3, this means that here I'm creating a matrix that contains 1. It has a dimension of 3 by 3. Okay? Divided by 9. So this one is which type of filter? Average, yes. It's the average filter. Okay? The other type of filter here, I will use the function, the ready-made function in the that exists in the MATLAB, which is called F special. So here it will create the Gaussian filter. Okay? And its size actually it will be 5 by 5 in this case. So here we have, if you want more information about the F special, so just go to the help page. And here in the help page, either you specify the type of the filter, or you need to specify the type with some parameters. Okay? In the case of the Gaussian, let's take an example of Gaussian. Here. Gaussian, this is the type of the filter. It needs to be mentioned between single quotes. H size, this will give me, for example, the size of the filter. In most of the cases, the size of the filter is actually it's a square. So here we need just one value. So when I say 5, this means that it will be 5 by 5. The second 5 that exists in the F special that we have called, this corresponds to the sigma value. Okay? So, which is the standard deviation. So here in this case, this H2, it was created using this command. Okay? Now let's look at the contents of H2 here. As you can see from here, this is the central value. As you can see, the central value here, it corresponds to the maximum value. As you go further from it, the values are decreasing. But they are not decreasing fast. Actually, they are decreasing slowly because the sigma is high. Right? The standard deviation is high. So this means that I will have large fluctuations. What should be the result of adding all of these values together? Should be 1. خلينا كده نجرب. Let's see here. We have some H2. We need to prove this. Yes, it's 1. Okay. طيب. So this is the first thing. So here we have created these 2 special filters. Let's go back to the. Here we have this one. We have read the image in X. So the original image is something like this, which is X. X here, it is what type of image? It's an RGB. Yes, it's an RGB. So here we'll make a figure. I am show X. Okay. So this is the original image. What we will do next is that to make things easier, we will use the grayscale version of the image and we will apply on it the different filtering operations. Of course, we can make filtering on color images as well. Okay? But here to make things easier, we will do it on the grayscale image. So here, as you can see, Control C. So this is the result of the conversion, and this is the original image, right? Now I want to add some noise to this image. So we'll use the IM noise function that exists in the image processing toolbox. Okay? And here I will assume that this noise, it has a 0 mean and it has a standard deviation of 0.1. So this is a noise values that will be added to the image itself. Okay? So here we'll find. Of course, here we are just simulating that we have a noisy image. In real life, of course, we are not interested to add noise to images. Right? I am show. Let's see here the image after adding noise. It's called XNG. Okay? So this is the image after adding the Gaussian noise. Right. Now let's go to the
here in this part, I will apply the filter using the IMFilter function on the noisy image using the filter H1, which is the average image. Then after that, we will show this image. Okay? So this is the image that we have after applying the average. Let's make some sort of comparison between these two images. Oops. So this is the image before applying the filter, and this is the image after applying the filter. Okay, we can see that there is some sort of noise removal, but on the other hand, the image is much more blurred. Okay, because some of the details have been removed as well. Fine. Now let's apply the second type of filter, which was the Gaussian smoothing filter, and display the result. Here as well, you can find that the image is smooth and some of the noise has been removed as well. Okay? Now, what we will try to do next is that we will apply the median filter. And see its effect as well. This is the median filter. Actually, it didn't give a good result. If we compare it with the Gaussian, we'll find that the Gaussian is a little bit better. Of course, here, in order to describe let's say, the quality of the filtering, we may have a subjective way of describing it and an objective way. Okay, subjective way is by just seeing. Okay, by our eyes. Okay, when we look at it, we can say that this one is better than that one. But what will be the objective way? What will be the measurement that we can apply here? It will be the signal to noise ratio, okay? The one that gives us better signal to noise ratio is better, okay? But of course, to compute the signal to noise ratio, I should have the original image without noise, okay? Which will not be applicable if I'm applying this in real life. Okay? So in this case, what will be applied is merely the subjective way. Okay? Right. Let's apply the conservative, Ctrl+C. Of course, here the conservative filter, it does not exist in MATLAB, so we need to implement it. So here we have, this is the result of applying the conservative. Okay? So maybe in our next homework, I will ask you to just implement or give me a function that will take an image, and on this image will apply this, let's say, type of conservative filtering. So this is the result of applying this. As you can see here, we will do the same thing after applying this 4 types of filters on an image that is having a noise of the type of salt and pepper. So here we will just take all of these lines, just copy it here. Okay. So here we'll find that this is the result of the conservative, of applying the conservative filter. This is the result of applying the median filter. As you can see here, in the case with the salt and pepper, the best filter, it will be the median filter. Okay? Which is logical, yani. This is the result of applying the Gaussian filter. And this is the result of applying the average filter. And this is the original noisy filter with salt and pepper. Okay? So, Okay. So this is for the spatial domain filter, okay, or the spatial domain-based filtering. Okay, we have the 4 types of filters that we have seen together. Okay. Now we'll see the frequency-based filter design. So we'll do the same thing, but as you can see from this code, the filter will be constructed in the same way for the average and for the Gaussian, but we need to convert them using the fast Fourier transform. Okay. Then after that, here he's showing us the result of this transform using the mesh plotting, which is the 3D plotting, and using the, let's say, showing it as a normal image, okay, that has, let's say, 2-dimensional image. So here we'll see the following. We'll see. Let's apply it here. Control V. So as you can see, this is the average, okay, and this is the Gaussian. Okay, this is the average filtering, and this is the Gaussian filtering. Yes.
What did you put 1,000?
1024. As we have said before, here in order to have our filtering operation to be successful, what I will do here, when I transfer my filter kernel or when I transfer my image, actually both of them should be transferred to the same size. So here we have selected the target size after transfer, it will be the same here, 1024. And if you look at the, maybe you don't have enough time to show it here, we can give it a small hint next time. If you look at the transform of the image itself, as you can see, this part. Here we'll read the image, convert it to grayscale, get the information about its original size. Okay? Then after getting the information about its original size, I will activate the noise. And the important part here is that I will transform it using the fast Fourier transform with the same size as the kernels of the filter. So that afterwards it will be easy to do the multiplication, element by element multiplication. Okay? So that's fine. So what I want you to do is to complete this example at home, okay? And next time, please bring with you your laptops so that we'll make some sort of hands-on session. We'll try to solve some of the problems that we have in the book, okay? The different chapters that we have covered, okay? The exam will be until the end of this chapter, yes. Okay? Okay. So we have Afnan, Aisha Radwan, Aisha Haj, Dana, Hanin, where is Hanin? Maha Ibrahim,
Yes.
Maryam is here, Noor Abu Nama, Noor Salim, Rahaf, Razan, Reham, Riman, Salma Hafiz, Salma Tariq, Turkiya. Okay.